Hello and welcome back to Calculus 2, yes, section 8.2 on integration by parts. So in math schools, in hallways, it's known, if in doubt, integrate by parts. It's a very important technique. You guys learned U sub. U sub was backwards chain rule. Integration by parts is backwards product rule. So we can derive integration by parts formula starting with the product rule formula from Calculus 1. So, but if you know integration antiderivatives, so those derivative techniques should have their backwards techniques. So integration by part, backwards product rule. So in Calculus 1, you learned that the derivative of u times v, that's two functions, is equal to u times dv dx plus v times du dx. So this is something you guys learned in Calc 1. What I'm going to do now is I'm going to integrate both sides. So I'm going to put the integral dx, integral dx, integral dx. So when I integrate everything, because it's a plus on the right-hand side, the integral will distribute on each of the terms. And now, if you take a look, the derivative and integral cancel. Now on this side, the dx and dx cancel. So what you are left with is, on the left-hand side, you have u times v, and on the right-hand side, you have integral of u dv plus integral of v du. So now all I'm going to do is move this to the other side and get uv minus integral of v du equals integral of u dv. There we go. And now we're just going to say integral of u dv is equal to uv minus integral of v du. This formula is known as integration by parts. So you see it being derived from basic product rule. U is a function of x. V is a function of x as well. So these are not just uv numbers, these are uv functions. We could have done this with f and g. There's no difference, right? Where you want to say integral of f dg is equal to f times g minus integral of g df. But we are not used to using df and stuff like that. So we use u and v because they look more like a substitution. There is another interpretation for us to derive this playing with the graph and the fact that you can integrate in terms of du and integrate in terms of dv. You can derive the same formula graphically. So we can do this. Let's go like that, let's say. And now you have your u-axis, your v-axis. Now this puppy here is du, and this one over here is dv. Now, the function you have here, this is not f of x, obviously, because this is u and v axis. We are going to take a look at the orange area and blue area. Orange area, A1, is going to be integral of, see, the v-axis is a function, so it's integral of v, and u plays the role of x, so v du. You also see du here for orange. The blue one, area 2, is integral of, now for the horizontal one, function is u. So u and dv, which you can see right there. So you have two areas, orange area and blue area. Now you also have a black area, which is everything, and the black area is simply how much you go out in u times how much you go up in v, which is represented by the total area inside the rectangle. So this is dimension of u, this is dimension of v, so the total area of everything is u times v. And now you see that all of blue plus all of orange is all of black, so you can write simply equation that area is equal to a1 plus a2. From there you have uv equals the integral of v du plus integral of u dv, which is exactly this line over here, and you just fish out u dv equals the rest and you're done. So integral of u dv is equal to uv minus the integral of v du. And again, the same formula, but we derived it differently. This time we actually made a graphical argument of adding two areas together to get the total area, which was u times v. So this is what we have for the theoretical part. So we know it's backwards product rule. We derived it from product rule, and then we derived it graphically from the perspective of just working with two areas. Now, the question is, what is this good for, right? So yesterday, we talked about, there were three problems in a row, and one of those three problems I said you will learn tomorrow, right? So we had the fact that y was equal, integral of sine x dx. We had integral of x sine x dx and integral of x sine x squared dx. So single x and then x times sine x and then x times sine x squared. So the first one on top was basic integral. You learned this in Calc 1. And the one on the bottom was the u sub, which was 5.5, also Calc 1. The one in the middle was the one that I said 8.2, integration by parts. Wait, we are going to learn this tomorrow after test. Well, it's tomorrow. So, what is the procedure to calculate the integral of, let's say, x sine x dx? By the way, Lab 2 addresses this very carefully over many problems and many examples, asking you to make wrong choices to see what goes wrong, asking you to make good choices to compare them to bad choices, so you can quickly spot bad choices. All of this is a whole bunch of experience. A lot of experience in doing these, just like a lot of experience you needed for chain rule and product rule and everything else. This is, again, a lot of practice, and it looks weird when you start. So here we go. Your job is to break this into two parts. So it's like a substitution. You are going to have, in this case, u equals x, and dv equals sine x dx. Now, you might ask why, and I would just say, I have a lot of experience. That's why. Now, you will acquire that experience as you practice the homework and everything else. So, please note that entire integral is broken and placed somewhere. There are no leftovers. Remember that you are allowed to have some leftovers when you do u sub, right? And then hopefully it works out later. For integration by parts, 100% of that integral has to be assigned in those two. Clearly, dx will always be hanging out in dv. So now, you differentiate du. So this part is the same as like u sub, right? So you have u, and then du is equal to, in this case, dx, because the derivative of x is 1. And on the other side, you have to integrate, because you need v. So d dx, let me write it in blood. D dx here, integral dx here. Now, when I integrate sine, I will get negative cosine x. And we do not have to put plus c, because there will be a major plus c at the end of the problem, because we have no limits. So you don't have to worry about plus c within the substitution part. So now we have all of the pieces that we need for our formula. Let me write the formula again in orange over here. It says integral of u dv is equal to uv minus integral of v du. So when I put this thing together now, I see that in here, right, this is my u, this is my dv. So this whole thing is this, right? I need to compile the right-hand side only. So we start by u times v. So u times v is x times negative cosine x. And then minus from the formula. So u is x, v is negative cosine x. So this part over here is u times v, and then I have the minus from the formula. Now I need integral of v du. V is negative cosine x, and the du is just dx. So this is now integral of v du. V du. This line is just you plug in. Guys, what I need you to see right now, Control C, Control V. Control C, Control V. No calculations. Control C, Control V, Control C, that's all you do. Copy and paste. The same thing for this one. This is your Control V from V, and here's your du. So just copy and paste, no calculations. The only calculation you guys did so far was to take the derivative here and to integrate there. That's it. To write the integration by parts over here, all you need to do, Control C, Control V, copy and paste all of these in their place. Now that you have this, you clean it up the best you can. So the negative jumps out. You have x cosine x. Minus and minus is plus. Integral of cosine x dx. And look at it now, right? The procedure changed the guts inside the integral, and now it's just integral of cosine, which you can integrate. What's integral of cosine? Very good. So negative cosine x plus sine x, and here is your plus c at the end. And this one over here is the answer to our problem. Now, as it usually goes, let's say you care, so you will differentiate your answer to make sure that you are getting what we started from, right? So to check, you take the derivative of negative x cosine x plus sine x plus c. No one cares, that's going to be 0 anyway, but for sake of completeness. So what do you have over here for this check? Well, you have a product rule on the first term, so copy the first, derivative of the second, negative sine x, plus copy the second, cosine x, minus 1 is the derivative of negative x, and then plus derivative of sine is cosine x. So you see that negative x times negative sine is x sine x, and then negative cosine and positive cosine cancel. Right? Done. So we did get what problem initially had. They match. Right? They match. So we know that our integration went just fine. There is a cute trick to remember the formula. If you always write u and then dv like this, and then you take those calculations down, if you organize it this way, then you can just draw an arrow like this, which shows you the formula. Do you see u and v connected? U times v, and then you see v du. And this is flat over here to signify a minus. Good. So if you draw the arrow like this, you see immediately uv minus v du. And that's your formula. So this was the introductory example for integration by parts. We have time to work out on one more. Tomorrow, we are going to spend more time with this to do a lot of examples. We also need to do definite integrals with limits, because that's also the part. And in addition to that, we need to take a look at some more advanced calculations. So let's take a look at another example. We'll do something else that it's kind of vanilla. We don't have to work too hard. How about integral of 3x e to the a to the x dx. So this is another integration by parts problem. Can't use u sub because you need x and x squared, right? If you want to have function derivative pair. So this is the problem like that. Now what we are going to have is, first we are going to kick 3 in front of the integral and not be concerned with that 3 at all. When I write in my integration by parts will fit in the parenthesis everything multiplied by 3. Right? So for integration by parts, we are going to assign x to u, and dv will pick up e to dx dx. Now, why am I making choice of u equals x? Because if that x wasn't there, problem would be a joke to solve. Do we all agree? Right? We all agree. Integral of e to dx is e to dx, end of story, right? But because this x is there, right, we have an issue and we have to use this method. So why am I choosing u equals x? I'm choosing u equals x because when I differentiate, derivative changes that x into 1. So technically it kills it, right? Which is the reason why I chose polynomial to go in the u part. U part is getting differentiated, and because the u part is getting differentiated, it will kill that x. And now v, when you integrate, remains the same, which is e to the x, right? Integral of e to the x is e to the x. Now we put our handy dandy arrow over here that helps us with the formula, and you go and you say, okay, u times v, that's x e to the x, minus the integral of e to the x dx. and we have this parenthesis closed because the 3 in front has to multiply everything. So now we have 3xe to the x minus 3e to the x plus c. And as it goes, you kick 3e to the x in front, x minus 1 stays, plus c for your final answer here. Now, you've seen a problem with sine x, and you've seen the problem with e to the x, and they were pretty much identical. I chose u to be x, and the rest to be dv, and then I worked out the problem. It's not always going to be like that. You are not going to automatically choose u equals x. Well, you might even not have x in the problem. It might be x squared there, right? So we'll see a whole variety of problems come up next time, but you have at least a little bit over here to start looking at the homework, go to study plan, practice some things, this weekend, right, you need to review if you had issues, right, if you felt like the exam had some integrals that you can't solve or something, that just means your Calc 1 is not good enough. And you need to review sections to help you with integrations. I told you 4.9, 5.3, no, 5.2, and 5.5. Those are the study plan sections that you can practice from Calc 1 to learn basic integrals, definite integrals, and u sub. Now, in addition to this, you might need to review product rule from derivatives to understand if you forgot the formula for product rule. So to this list of sections, add product rule just to make sure that, because as I said, maybe you want to check this answer, right? Well, you have to use product rule formula to take the derivative of it. And if you don't know or remember product rule formula, you can't check the answer. So that's all for today. On Monday, there will be a part 2 for this lecture. And then after that, oh, hold on. After the lecture on this, on Monday, we have the lesson on trigonometric integrals. So your weekend is also going to be filled with basic trig identities, ones that I mentioned on the day 1. I did not write those down. I had them written on the board, and a whole bunch of you took pictures of the whiteboard with those formulas. Now, I might have in calculus from earlier, intro, great. Here it is. So, I'm not sure, did it switch? Where's the trig? There it is. Would it be helpful if I post these notes from before? So basics of trig. Review this because trigonometric integrals, next class, Monday. Tuesday, we go with the trigonometric substitution. So 2 sections back to back, and you see the trig kind of sneaks into every other section as you go along with these. So you need to review trig. These are the basics, the triangle, and setting up 6 functions regarding which side. This is going to be extremely important for trig substitution. And I have seen that Evan talked about it. If you care about the values and to learn the values, you can. Here are the almighty almighty power-reducing formulas that you absolutely must know. Remember, we have similar ones when you swap this for hyperbolics. Here it is an example of problem being done, which is a calculus 1, because you are using a pre-calc identity, and then you're just integrating a half and integrating cosine. Those are basic integrals. And you are going to need to know these red formulas. So power reducing and these red formulas are absolute must for trigonometric integrals, because we will be using a lot of Pythagorean, these are called the red formulas, Pythagorean identities. And when you consider the flips, you have 9 of them. 3 main ones, right? And then when you shuffle those around, you get these. You see, sine squared is 1 minus cosine, right? 1 minus cosine squared. Cosine is 1 minus sine squared. So 3, 6, 9 all together. And we'll use all of them, right? Now, luckily, they are the same because they all pair the same way. You have sine paired with cosine, tangent with secant, and cotangent with cosecant. And you can derive these by dividing this one by sine squared everywhere. Sine squared divided by sine squared is 1. Cosine squared by sine squared is cotangent square. And 1 divided by sine squared is cosecant square. If you divide through by cosine square, sine divided by cosine is tangent. Cosine divided by cosine is 1. And 1 divided by cosine is secant, right? So it will be very helpful if you guys review this, so you don't fall off the truck during the lecture. So Monday is going to be very important. Make every effort that you are here on Monday at all costs, other than death, obviously, in that case, doesn't matter. We'll set up a lot of stuff for Chapter 8 in that one class. So see you then.